Okay, perfect. So I think everybody could hear me right now. We're gonna start the session now. So you guys have the chat. How I tend to do this, I'll try to explain the topics I want to cover up today in the session. I'll try to be slow, because it's new stuff, and because I don't have you in person, I can't take the feedback of how I look at your face and I get the feeling that you get it or not. So I'll try to keep it slow. And if you have any questions about those things, you can ask me in the chat, right? I can pause and I can address those questions depending upon how I receive them, okay? And yes, there is audio. I think Rain's not able to hear it. If you guys can hear it, can you just tell me in the chat that everything's good and we can start? Like I said, Anna can't hear it. I think you gotta probably... So the people who can't hear it, I think I have it turned on from my end. You probably have to tweak a little bit on your app. Try to see if you haven't muted anybody. Or if you go up to the meeting, you can turn on participants. And you click on that. There's going to be a little mic in front of my name. The mic should be having gains on it. So there's a lot of people who can't hear it. Okay, let me try to fix that first. Okay, try to do that. Go to the participants, and there should be a mic there. And make sure that I'm not muted over there. Once you can hear me, you can confirm it back so we can begin. If you can't figure it out, please post it in the chat so I know. Okay, there's somebody who can hear it. I'm waiting on the people who weren't able to hear it. Okay, I think unmuting solved the problem for most of them. Okay, perfect. All right, so let's get into it. So the topics that I plan to cover today are going to be the next topic that you're going to be studying over there. So there's going to be, so this, just to inform everybody out here, I have both UBC and SFU students in the same chat. The topics that you're going to study are exactly the same, and so is the curriculum. So I'm not going to be answering any specific course-related questions for now. If you have those things, you can definitely talk to me on Facebook. But what I plan to do today is introduce you to topics, get you started on the things that you have. So both UBC students and SFU students have their homeworks due, and they both require this information in order to begin that homework. So we're trying to make sure that I cover up all of them, the topics at least, so everybody can get a start on this, right? So topics we're going to cover today is the Riemann sum. Okay, and that's just a natural extension of what you learned before. Okay, so far both the courses I've been learning how to express things in summation, how to navigate through those kind of things in algebra, and how do you perform different operations, how do you find the sum of certain things. So that knowledge was required in order to come up here and solve this topic. Okay, that's the only reason why you study that thing. Okay, and eventually from Riemann sums we're going to jump up to what is called an integral. So I'll bridge that up right now in front of you. We'll do a couple examples and it'll make more sense, okay? So, what we're going to start off with is the idea. Okay, so what is a Riemann sum and why did this guy even think about doing it, right? So the problem that he's tackling is we want to compute the area under the curve. okay? Because sometimes what happens is there are weird shapes in nature that you can't just calculate the area of, but you can represent them mathematically to get the area. And why do you think we need area is for different applications that you'll be studying in this course, okay? So this is a challenge that we want to solve, and we want to figure out what's the area under a curve. An example that kind of motivates you towards doing this could be just like if you have, let's say, a leaf, right? And you probably saw this example. So you have a leaf and you're trying to figure out how much oxygen is coming out of this thing, per minute or something like that, to just compute exactly how much chlorophyll is there in this leaf. And all those trivial examples that you think of will require you to have what is the area of this thing, right? So if you think about it this way, what you can see is you can kind of like represent this leaf on this XY axis, right? And model this as a parabola. So that parabola, the portion that's above the x-axis is like this portion, and we're trying to find all of this area, right? And that could be modeled as like a parabola cutting the axis. So we can use mathematical tools to identify that. So that is what this guy's trying to do, okay? How he's going to do, so we're going to work through his procedure. Procedure, like on a very bigger scale, to fit easy shapes. So you'll try to fit like the shapes that you're familiar with, such as like circles, triangles, rectangles, squares, and then try to like see if you can kind of approximate the area under a curve, just like an educated guess. So that's what we're going to try to do. But there's going to be a lot of steps involved in this. So Reimann took an approach which is very specific, and that's what we're going to talk about now, okay? So the shapes they're going to fit are going to be rectangles, okay? How many? That's up to you. So why I said depends is if you want to keep your calculations easy, what you can do is just approximate roughly using the number of rectangles you can solve in your head. That's good enough. But if you want more accurate answer, the more accurate answer will be given to you if it fit in more rectangles, and I'll show you exactly how it works, okay? So the number of rectangles depends upon the accuracy that you want to achieve. And at the end of this, what we're trying to do is achieve as much accuracy as we can. So we'll involve limits at the end, okay? So let's start off with this. Does anybody have any questions on the motivation part of this thing? So everybody should have a clear idea of what we're trying to do with the Reimann sum, right? What's the idea? And how we're going to do that is by fitting in more shapes. Is there any questions? Makes sense. Good, right? Okay. Excuse me. So we're going to start on actually doing this work. So don't worry about this PDF. You're going to get this PDF. I'll send it in the group so you can access this, okay? All of these files, all the notes that I'm taking in this video will be up there. So don't worry about it. Just try to focus on understanding what's happening. So I think it's better to start off the example by considering a very like a familiar function that we have, and then we'll start to set up the Reimann sum in steps so it will make more sense. Okay, so for this example, I'm going to consider a very simple function where f of x is just x squared. Okay, so we're going to find the area that's bounded under the curve fx equals to x squared from two bounds. We're going to specify the starting point and the ending point, because you can't just find the total area all the way. So you have to specify which area you're trying to calculate. So the starting bound is represented by A, okay, and the ending bound is represented by B in this case. And I'll show you what it looks like on the graph. For now, let's say if our A is going to be 1 and our B is going to be, let's say, 4, okay, something like this. And we're going to try to like make sure we can kind of visualize the picture of this. So let's see, if you were to draw this the area that you're trying to achieve here. So that's your x-axis. That's going to be the y. The graph, because we're only sticking in the positive quadrant, I'm going to draw only this portion of this. Okay. And then what I'm focused on is to find the area from 1. I messed it up. 1 up to 4. Okay, that's what we're trying to achieve. So far we're going to try to achieve this figure. So I'm going to zoom in a bit so to kind of explain you what I'm trying to do. The area that we're looking for is going to be all of this area. That's inside the zone. Okay, just to kind of visualize. I know that's not as accurate as I can, but yeah, you get the idea. So now it comes up to our choice. How many rectangles do we want to fit in to make it accurate? Okay, just for this example right now, what I would kind of suggest is we stick with a very basic number. So I'll take 3 for this chance, right? So I want to fit in 3 rectangles. So whenever I specify the number of rectangles we're going to use, this automatically becomes a finite Riemann sum. Okay, because I know the amount of rectangles I'm going to add. Okay, that's just a fancy name. And at the end of this thing, you'll know there's an infinite Riemann sum as well, which you need to know about. Okay, so I'll talk about that in a bit. So far, we got to fit 3 rectangles. So now the procedure is very straightforward. So for 3 rectangles, a rectangle is a very basic shape. So the only thing you're worried about is the base and the height. Okay, in this case, so the base of the rectangle is going to be fixed. Okay, base is going to be fixed, and we're going to call that delta x, because that's the difference we have on the x-axis. That's what we call delta x. So that base has a delta x definition, and we're going to split up the whole domain into equal parts. Okay, we're going to make sure that we understand this. The base for all these 3 rectangles are going to be the same, and it's going to be delta x. By definition, it's always going to be splitting up all of this zone from 1 to 4 into equal parts. So now we have 3 rectangles we're going to fit in. How much space do we have? We can calculate the space by doing b minus a, because that's this zone. So this whole space is 3, basically, right? So that's b minus a. And you're going to split all of those distance that you have into equal parts. And that depends upon how many rectangles you're fitting in, right? So this right here is called n, where n is the number of rectangles, right, in this notation. So delta x is by definition always fixed to be this. So please remember that this is fixed. Okay, there's no doubts about this. This is definition. It doesn't change when you change things in the future. Okay, so you have fixed the base, and by definition that delta x is defined as b minus a over n. So let's now try to draw it visually. Okay, when you try to draw visually, you know you got to fit in 3 rectangles, and the space you have is 3 units here, right? So basically all you need is your delta x going to be 4 minus 1 over 3, which is 3 over 3, which happens to be 1. Okay, any questions so far when we try to fix the base of each rectangle we're going to fit in? I think everybody's on the same page with me, right? So we're good. What I'm going to do now is I'm going to try to make this here. Okay, so we have 1, we're going to have 2 here, we're going to have 3 here, and then we have 4. So that's like the rough picture we're trying to draw, and these are going to be the spots where we're going to have my rectangles all together. Okay, so we're going to fit in 3. So now another part is the height. Okay, so that's this base. Now we're going to talk about the height. Height of these rectangles is dependent upon how we pick the point. Okay, so there could be 2 ways. There are 2 possible ways. Okay, One way is to actually use the left hand point of the base to pick as your height. Okay, so if you pick the left hand point, that means you're going to use this point for this rectangle. So if you're going to fit in a rectangle here, all you got to do is choose wherever this thing intersects this point as your height. And then you go all the way here and you come down. Okay, this is the rectangle that you can make with choosing the left hand point. How about if I was to use the right hand point? So then you pick up this point, you go all the way up here, you come down, and you just come back like this. Okay, so this is the fundamental difference between two choices that you have. You can either pick the left or you can either pick the right. Okay, for the sake of like this specific example, I'm gonna use the right hand notation. Okay, just to like give it out here. So my rectangles here are gonna look something like this. So I'm gonna try to use this fancy color. So in this rectangle here, we know this base is delta x, that's fixed, right? And what we try to do here is to make this rectangle, we need to use the right hand point. So we're gonna use this point as my height point. So we're gonna get all the way to this function. Okay, all the way to this function. This value right here is going to be the height of my rectangle. Okay, and this point right here could be easily figured out by using the function. I'll tell you exactly how to write it. But now, how do you complete the rectangle? You got to come back. You got to keep going down all the way to the front one. Okay, so now in this case, you see the relevant area that we're trying to include here is all of this. Okay, and that's this portion. But we do have this extra, that we don't need. This zone, it's just like an extra area that we don't need. So is there a way for us to avoid it? For now, in this case, we don't. Because we can only use the left or the right hand point to kind of fix our ideas. For us, right now, this is how we take it because it's just an approximation. Okay? I'll show you exactly how you make this approximation into a very accurate answer later on. Okay? So everybody gets the point that we're trying to include the pink area and we're trying to get rid of the red one. Okay? But we can't exclude anything so far, we just can approximate it. So we're going to take this rectangle's area like it is. Okay? So we're going to call this rectangle the number first rectangle. Okay? That's the first one. Now, the second thing we're going to do here is we're going to still use the same convention to write the other rectangles that we're trying to make. So now, again, the base is still fixed. Again, we have the same delta x base down there, the fixed to be 1 units. Now, the next time we're going to put the right-hand side notation, we're going to use this point because for this rectangle here, for this rectangle that you're going to make here, this is the right point. Okay, this is the left. For this rectangle here, this was the right point, this was the left. So we're going to keep that in mind. Now we're going to keep on sticking to the same notation. We're going to use the right hand side again. So now this height would be all the way here. Okay. So now to complete it, you got to go back, come down. Okay. That's how you fit in the second rectangle. Now in this case, again, the relevant area that we want is all of this, but we don't want this area out there. Okay, that's like an extra error that we have in our areas. So we'll construct the second rectangle. We're going to call this number 2. The third rectangle is going to be based on the right hand point here. So now the right hand point that you have here will be this one. Okay, so now we're going to make a rectangle here in this zone. This will be the right hand point of the rectangle. The base is going to be the same. Delta x base. And then we're going to have this as our height point. So I already drew that out there. I'm going to use that same line to make that rectangle, right? And then we're going to go back here and come back down. So now the area that we want to include is all of this, and the area that I want to exclude out of this is this, right? But we can't do that right now. It's just what we're going to get for now. Okay, this is going to be called a rectangle 3. Okay, so we're based on 3 rectangles. We're going to add this up. The idea we're trying to achieve is we're trying to say the area under the curve is approximately equals to the area of these 3 rectangles. Okay, that's the idea. So now just going to label these heights so that I have a better idea. That's the height of my second rectangle, and that's the height of my third rectangle. Okay, so I'm going to call this h of 1, h of 2, h of 3. Okay, base is fixed, so we can now go ahead and compute this. So until this point, is everybody okay with me? And we're on the same page. We're trying to find the area under this curve. We're going to approximate it using 3 rectangles, and the setup that we're going to do will look like this. So first of all, you got to pick up the base. So the base is fixed to be b minus a over n. So we figure out the base has to be 1 units, right here. And then we have to figure out the height. We had 2 possible ways to go. We can either choose here, so I'll show you. We could have either chosen this to figure out our height point, or that to be our height point. If I would have chosen this, then my rectangle, should look like this, right? But because we picked the right point, our rectangle looks something like this. So we picked the second one just for the explanation part right now, and we're gonna compute all these individual areas now. I think everybody's on the same page with me. If you have any questions, please ask me right now. Okay, I'm not getting any questions, so I think everybody's good. So now, how do you compute the area of these 3 rectangles? We're trying to say the area under the function x squared from x equals to 1 to x equals to 4 is approximately equals to the area of the first plus the area of the second plus the area of the third. Okay, right? That's what we're trying to achieve. So try to find the area of the first, what we have to do here is write the expression for the area of a rectangle. And that expression is very easy, which is just going to be the base times the height. Okay, so the base is defined as delta x. So I'm going to use the symbols for now. The base is delta x for the first rectangle. And the height for the first rectangle we're using is h1, right? Because that's the height. Second thing you got to do is, again, the second base is still delta x, doesn't change for the second rectangle. The height, however, is height 2. Okay, and then plus, you have another one where you have delta x times height 3. So we got this part. Now, as you can see in this expression, delta x could be easily factored out. So I can write this whole expression again with delta x factored out outside. And in the inside part, we have height 1 plus height 2 plus height 3. Right? And if we can evaluate those heights, we can easily find the area, or like at least the approximation towards the area. Okay? So now we have to figure out what's the height going to be. I think most of you guys already know this, but I'm just trying to make baby steps here so everybody is on the same page with me. This height here is whatever is the function's value at this x. Okay? So I can literally write this as f of 2. Right? Because 2 is the x coordinate where I'm trying to find the height at, and the height is just whatever the value of the function is at that x point, right? So that's f of 2. The next one, we're going to use this as our point because this is literally but nothing but f3, right? And then this one is going to be f of 4, similarly, right? Because this is the point we're considering. But what we trying to do here is we trying to generalize this whole situation here. Okay, the general idea here we're going to put is we want to express all of these 2s, 3s, and 4s in like reference of delta x. Okay, because that's the increment happening every time, right? The reason why we're making this is we're going to make sure we make a general formula that we can apply to different ideas later on in the course, right? So how would you express 2 as a part of delta x? So you have to think about it this way. I'm going to use like a different color here. So this point was my A point, right? Theoretically, that's my A. It's 1, but so far if you don't have any number there, symbolically you can call that A, right? So that's my A point and that's my B point. Because everything is just an increment of delta x, so for the first rectangle, this spot right here could be written as A plus delta x, right? Because you're having addition of this delta x portion down there to A, and you get to 2, right? In this case, it makes sense because A is 1 and so is delta x. So when you add 1 to 1, you get to 2, right? Is everybody with me at this point? I want to make sure everybody is. Okay, this is very crucial. This makes sense, right? If you have to express the other coming coordinates in terms of A, all you're doing is adding a delta x to them, right? Similarly, this point could be expressed as you have A plus twice of delta x, because this time you literally added 2 times off that distance, right, to get to 3. And then the last one could be expressed as A plus 3 delta x, right? And you got up to that point. So a couple of things I want everybody to see here is that this number is 1 times delta x, then 2 times delta x, and then 3 times delta x is the increment happening, and that depends upon how many rectangles you're going to put in. So that's the symbolic general form. Okay, so that's what I'm going to do here now. I'm going to express these heights in that kind of realm, okay? Because we put that down there, we're going to make sure that I show you how to write that here as well. So this delta x will stay here. Okay, that's the same, not changing at all. This height right here, the first one is going to be just f of A plus delta x, symbolically, right? We can put in the numbers, but for now, we can stick to symbols. Plus the height 2 is just f of A plus 2 delta x. And then plus, the last one is going to be f of A plus 3 delta x. So I'm going to pause for a minute here. Everybody should be on the same page. Please ask me any questions if you have so. Okay. I haven't used the function x squared yet. I haven't used the a value to be 1 yet. I haven't used the value of delta x to be 1 as well. So all I'm doing is just a generic symbolic way of representing this sum. Everybody's good with me on this? Okay. Nice, so we can begin now. Now what we'll have to see is the changing pattern in these summations. This is where all the knowledge that you did before comes in handy. Okay, if you look here, in this summation right here, okay, the only thing that's changing and that's being incremented eventually is just whatever the coefficient of delta x is, right? Delta x coefficient is 1 here. Next summation becomes 2, then becomes 3, right? Everything else stays the same. So if that's the case, what you can do is you can express this as a summation. Okay, so we can cook up a summation variable and we can represent this coefficient using that variable because that's being incremented by 1, right? So I'll show you a bit more clear. So what I can write here is that the area we're trying to calculate is delta x. And now instead of having like a single sum, what I can do is I can use summation sign. So that's being multiplied. This summation sign, where my summation variable is I, okay, it starts at 1 and it goes up to 3. Okay, and this here is going to be f of a plus I times delta x, right? So this expression that I just wrote here is equivalent to what we had before, okay? and you've been working on this before with your assignments and homeworks, where you have to convert a sum into a summation notation, and you have to sometimes convert a summation notation into a sum. Okay, that's just like a neat way of writing it. Okay, so is everybody okay with this expression right now? So, okay, yeah, so why does it go to 3 if b is 4 is a valid example. So all this work that we're thinking, why does b relate to this number, is already done before. Okay, so if you come back here, the height of the rectangle that we're going to get here with the b is going to have a very specific x coordinate here, and that's a plus 3 delta x, right? Because you're just adding 3 increments of delta x to the value a that you began with. So now, keeping that in mind, if that was clear, all we did is we just made this sum up here like this, right? So that's going to have a a plus 3 delta x. So in order to make my summation make sense, I need to have my I starting at 1 here, then going to 2, and then ending at 3, right? So whatever the b value is kind of irrelevant in this case, because it doesn't go up to b value. There's no physical relationship for all these things. It's just a conceptual way of putting up the idea, right? I have a 3 here because it takes me 3 delta x's to reach from a to b, and that is why I have a 3 up top here, because that's what I want my I to be finally at. Does that answer your question? Okay, perfect. So let's go. Now, this is all what you need in order to evaluate this whole thing. Okay, so now I'm gonna put some more symbolic mess up here. It's just how professors like to do it, and because this is such a very specific topic, what they tend to do is they ask you exactly with the notation that they asked you in the lectures to answer questions on the exams. So I want to make sure everybody's aware of the notation. Okay, so now notation work is all in blue. What they tend to call this whole thing inside is x star of I, okay, or sometimes xi. Okay, there's just multiple notation of different books. All this means is that xi is just some x that's dependent upon I, right? And that's easily visible here. So it's a plus I delta x. That's the definition, okay? And delta x is just b minus a over n, okay? Symbolically, that's the fixed definition of this Reimann sum, okay? So now, if you were to kind of understand this symbolically, you know that n was 3 in our case, right? And that 3 eventually ended up on top of the sum. So when you're doing a right-hand point setup, you have to see that the top bound is also n, right? Because that's the number of rectangles you're going to do, and that's the number of delta x's you're going to add, right? So the general form of a Reimann sum, okay, I'm going to write it down here. For, let's say, a function f of x from, let's say, a to b with capital N rectangles is going to be written like this. So that's going to be a summation, because this delta x is going to be a constant, right? It's going to be a b minus a over n, a number. So it doesn't harm to put this inside with this summation, okay? So that we have like a nice standardized form that we have. So this could be written as the Reimann sum, capital R, sometimes they use it, is defined as a summation from I starting to be 1. So this is a very specific, this is a right-hand notation. If you pick the right-hand points, and it will be specified in the question, to pick which one they want you to pick. If it's not specified, then you can just choose whatever you want. Okay, and if you're given the opportunity to choose, always choose the right, and I'll show you exactly why. Okay, so right hand point, you go from I equals to 1 up to n, because remember, symbolically that was just as a representation of n, from 1 to n of delta x times f of xi. This is the formula that they want you to remember. Okay, in which, by definition, delta x is always going to be b minus a over n. So you're given the a, you're given the b, you're given the n, so you can put them down there. B minus a over n. I should use small n here, because to just avoid confusion, because everything is in small n, right? This, and then xi is always defined to be a plus I times delta x. So once you figure out what delta x is, you can plug that in there, and you plug the a that you already know, and just have an I hanging out there, will be giving you the actual equation, right? So now, this is the general form. We're going to go back to the problem that we were solving. So right now we have this whole setup, right? We know our values, we can plug them in. So let's go back here. I'm going to try to go to the next page. So what we were trying to evaluate here, in the green, was I starting from 1 up to n, which is 3. In this case, I'm going to put in those numbers. Delta x is nothing but 1 times f of xi, right? So first of all, let's compute what xi is going to be. Xi by definition is a plus I times delta x. So a in our example, if you remember from the beginning, a was just 1. Okay, so we're going to stick to 1 here. So a is 1. I is just I, because that's the variable of summation. It's going to change its value later on. So that this, and then delta x is 1. So literally, this is what your xi is going to be. Right? So if that's your xi, and you know f of x is just x squared, then what's going to be f of xi? It's literally, you plug this whole thing in for x, right? So my f of xi will look like 1 plus I squared. And if you expand this, just to make it look nicer for the later parts, you'll get 1 squared plus I squared plus 2I, right? Standard form, I squared plus 2I plus 1. Okay, so this is my f of xi. So all I got to do is take all of this and put them there. I know my delta x. So my summation now is becoming one of the problems that you already solved before. 1 times I squared plus 2I plus 1. Okay, and this is just something that you guys have already seen or done before in all the web works and the homeworks that you guys did before. 1 to 3 of I squared plus 2I plus 1. And this could be easily evaluated using the summation formulas that you guys know. So summation of I squared, first of all, let's just break it down. Break it down into separate parts so it's easy for you to absorb. I squared plus summation of, so I can take this 2 out of the summation because that's just a factor for the sum, times I from 1 to 3 plus summation of 1 from I1 up to 3. So this, by expression, it's n times n plus 1 times 2n plus 1 over 6, right? And n here is 3. So it's 3 times 4 times 6 plus 1, that's 7, divided by 6, plus the other one is going to be 2. So the formula for summation of I is n times n plus 1 divided by 2. N here is 3, so it's 3 times 4 divided by 2. And then plus summation of a constant is just n. So n here is 3 again, so it's just going to be 3. So if you evaluate this, you're going to get 1, it's going to cancel out, become 2 here, So the first part is 14. This part is 12 plus 3. So 14 plus 12 plus 3. That's going to be 29. 14 plus 12 plus... I'm tripping. Just give me a second. So 14 plus 12 is 26. And then you have the 29. Yeah. 29. So that is the answer to this Riemann sum, right? So what we're trying to achieve here, the area under the curve y equals to x squared from 1 to 4 is approximately going to be equal to 29. Okay? Now is the time where you ask me any questions about evaluating Riemann sum. So everything up to this point should make sense, and then we're going to go move to the other questions. If you have any other questions, please ask me right now. Yes, so if you talk about the over approximation, yes, because you saw that we have these extra red portions that we don't need but are still there in our calculation, right? So this is, first of all, my over approximated approximation here, right? So that's an over approximation for sure. By how much, we'll figure that out later if required, okay? Second question is 29 is the sum of the under the curve. So 29 is literally the sum of the area of 1, 2, and 3 rectangle, right? So 29 should technically represent the area under the curve. So all the pink portion down here. So kind of like all of this under the curve, right? From 1 to 4. But because we have this extra stuff here, it doesn't exactly represent that, but approximates it. So 29 is the approximate area under the curve. Okay, that's this. And then what happens if n is unknown? Okay, that's a bigger challenge for sure. But because, as we talked about Riemann sum, you are trying to do the setup, right? So if you are trying to do the setup, you're the boss. So you pick what n you need. And that depends upon the level of accuracy you want to achieve. If they don't specify an n, what tends to happen generally in these problems is they want you to choose n as big as possible. So when we want to choose n big as possible, what you got to do is stick to the Riemann sum. That's an infinite Riemann sum, where n is infinite. You're trying to fit in infinite rectangles into this, but we're going to go there after this, okay? So hopefully that answers your question, if n is unknown. Usually it's not. It's always going to be fixed for a finite Riemann sum, and for an infinite Riemann sum, it doesn't matter wherever n you put, it's going to be infinity anyways. Okay, so either you know it or it's going to be infinity. So that's the easy way. And now what if you start at the left-hand point? So that's an excellent question now. What I want to do is I'm going to write a parallel here of how we're going to start for the left-hand point, right? So how many differences do you think we're going to get if we start at left? I'm going to use the orange color, okay, just to represent the left-hand point. So if you were to make a left-hand point sum, you are going to start here, right? Your rectangle is going to look like this. The first one is going to look like that, okay? So the height here, this height one, would be represented by whatever the value of x is here, right? And in this case, that happens to be just f of a, right? Does it make sense? Now let's jump to the next one. For the next one, we're going to make a rectangle using this left point. So we're going to go up here, and my left hand point is going to look something like this, right? So now my height here for the second rectangle is whatever the height was for my first rectangle before, right? And this is going to be your h of 2, right? For the second one. And what if you jump to the third one right here? You get the point, because the next height will be like right here. So you're gonna have this coming down all the way here. So this is f of a plus 2 delta x, right? And this is gonna be your height of third. So the key thing you gotta see, if you were to do the same setup with the left-hand point, your f of a plus delta x will be replaced by what? F of a, because that's the first height. And then the second height will just be f of a plus delta x, because that's the second one now. The third one is going to be f of a plus 2 delta x. So only thing that you see, the difference there, is that in this case, the coefficient of delta x is 0. And they're all shifted back by 1s, because whatever was 2 is now 1. Whatever was 3 is now 2, right? So they're all shifted back by 1. So this is an excellent way to observe this. You can write a Riemann sum that's a left-hand point equivalent here. Okay, this is the right-hand point. So I'm going to write right in green, and this one is going to be the left in orange. The only difference you're going to make now to write this summation, you want your I to start at 0 now, and you want it to finish at 2. Before it was starting at 1 because this was 1, right? Shouldn't do that. Because we had 1 here, 2 here, 3 here. We started at 1, we went into 3, right? Now the only difference we're going to have is this. We're going to start at 0 because this is just a plus 0 delta x, right? This, and we're going to end up at 2. So only difference you're going to see here is in the bounds. So this is going to start at 0 and going to end at 2 or n minus 1. Okay, that's the left-hand setup. The only difference you're going to have is just a change in bounds. Okay, so how does that change everything else? This is the right-hand point notation here. What about the left-hand point? So left-hand Riemann sum is going to be defined exactly the same way, delta x times f of xi. But your I here will start at 0 and will stop at n minus 1. So it's going to start 1 before and is going to be starting at 0. So f of a is not 0. What we're trying to say is f of a could be written as like this. So let me try to remove this here. Plus 0 times delta x, right? That's essentially just f of a. So what we're trying to do here is represent them in terms of delta x like we did before, just to make yourself more comfortable with the idea. Okay, the idea here was the coefficients start from 0, 1, 2. In the other case, it started at 1, 2, 3. So that's the difference between the left and the right hand point. Is it clear now? The left hand point, only difference is just this. Okay, so now let's move from this to kind of like the notes that I want to give you guys. So I'll show you those. Where do I have them? Should be in my files. So this is supposed to be it. Okay. So area as a Riemann sum, and these are the notes we're going to take up here. So what I'm going to do is I'm going to just do it right here. Copy this. I'm going to paste it here so that we can have a track of what's happening. So this is what it represents, okay, if you want to look at it. So summation set up to approximate the area under a curve using multiple rectangles and adding the individual areas. The number of rectangles are finite in a finite Riemann sum, okay? So let f of x be a function defined over some real number range where you start at some fx greater than 0. The area under the function would be given by the left point definition. Has the only difference here, as you can see, f of xi times delta x stays the same, doesn't change. The only difference between the left and the right is the bottom bound and the top bound. Okay. For the left hand point, you start at 0, you stop at n minus 1. For the right hand point, you start at 1, you stop at n. And that has to do with the shift in the left and the right notation. Because when you're trying to use the left hand point, your beginning spot will be f of a, right? So delta x, we're not going to be adding any delta x. So that's 0. But if you do the right-hand point, your beginning spot will be f of a plus delta x. So you have to add 1 of delta x to begin with. And the number of rectangles need to be the fixed. The same amount of rectangles needs to be there. This is n rectangles. So if you go from 0 to n minus 1, you're essentially adding n rectangles. And if you go from 1 to n, you're still adding n rectangles. Okay? And here, by definition, delta x is always going to be b minus a over n. And x of I is always going to be a plus I times delta x. Okay? And n is going to be number of rectangles. So now, any more questions on this? Just the formula of it, just the expression of it. We're going to do one more problem right now, okay, so that everything will just fall into place. Okay, that was just a theory part of it. I want to make sure I address it in detail so that everybody has an idea what we're trying to do. Now we'll try to solve a problem, like a real problem. What kind of questions did they get? Okay, so I'm going to take this problem here in the SFU worksheet and trying to solve this here. Okay, so now this looks overwhelming. Don't worry about it. What we're trying to do here is we have a function. Okay, we have a function here that's f of x is x cubed, and this problem we have like the area defined as a definite integral. So we're not going to go there yet. We're just going to stick to our happy land that we know how to work with. So essentially what they want you to do is you're going to find in the picture below, draw the approximate area if A using 4 rectangles, okay, of equal width with the right endpoint rule. Very important. So they've specified you what the end needs to be. They've specified you what the right endpoint needs to be. They've specified you the interval is going to be 0 to B. So they've given you the first number, that's A, that's 0, but they haven't specified what the next one's going to be, right? So we'll assume that's going to be some number. We're just going to treat it like that for now, okay? So in this case, you got to write the lengths of the base and the height of the third rectangle, which has the base x2 and x3. Okay, so this is how you kind of start this problem. But if I was to construct like an easier version of this so that I don't deprive SFU students from actually attempting the problem, I'll do the same problem, but with a number there for B. Okay, so we're going to use B as 4. You know, just for the sake of it. So I'm going to try to find the area from 0 to 4 using n as 4. Okay, so we're going to use 4 rectangles. We're going to do both left and right, okay? So to do both left and right, we need to make sure that we understand what's exactly happening. We know the only difference between the left and the right hand setup is just your summation going to start at different spots, right? Left is going to start at 0 and at n minus 1. Right's going to start at 1 and at n, right? So everything else stays the same. We can still find delta x, we can still find xi, we can still find f of xi. We can do all of those things, but we only need to just change the bounds to evaluate left and right. Okay, so I'll show you the right first, and then we're going to go to the left. So strategy is to figure out these things first. Okay, you got to figure out what these things are. Delta x and xi. Okay, once you have those, you can construct this whole thing and put it inside a summation. Okay, so that's what we're going to achieve for. Right now, we got to put down the information that we know. So we're going to put down the information we know. B is equals to 4. A equals to 0, because that's the bounds given to us. Okay, we know n equals to 4. So once we have all of these three, we can directly jump to delta x. So delta x by definition is b minus a over n, which is 4 minus 0 over 4, which happens to be 1. Cool, so we figured out delta x, we have the number. After we have delta x, we have to figure out xi. And xi by definition is always going to be a plus I delta x, right? So you know delta x, you can plug that in there. You know a, you can plug that in there too. So your xi is nothing but 0 plus I times 1, or just I, right? Very easy in this case. Now, what's next we're going to cover up is find f of xi. So because we want to achieve this formula here, let me just go back. So this formula requires you to know what f of xi is. So we're going to find that, and all we need is to plug that thing into this function. So if xi is just I, then f of xi is just going to be I cube, right? You just plug in the I there. So that was just as easy as you can ever get. Perfect. So we have I cube here. Now is the setup part. So now we're going to solve them parallelly, right? There's no difference. You need this information irrespective whether you're doing a left or a right hand point. So I'm going to do a right hand point here, and then I'm going to do a left hand point in parallel here. Okay. The only difference though is just the bounds. So here my I will start at 1 and go up to n, and n happens to be 4 in this case. So we'll go up to 4. And then f of xi times delta x. So delta x is 1 times f of xi is just I cube. Okay, so this is my setup that I want to solve to get the area under the curve approximated using the right hand point. Okay, and now for the left hand point, all you got to do is just same stuff, nothing changes but the bounds. Starts at 0, goes up to n minus 1, so it goes up to 3, and again 1 times I cube. Nothing changes, same stuff. Okay, so here what you can do in the right hand point is solve it right away. You know the formula for summation of I cube. It's a standard formula. Okay, so if I was to show you what that formula is, it's right here. Okay, so the formula is number 4. I cube formula is n times n plus 1 whole over 2 to the whole squared. Okay, so in this case we know our n is fixed to be 4. So we have we're gonna have 4 times 4 plus 1, 5 over 2 whole squared. That's the answer, literally, for the first part. Okay, and if you were to do the left hand point, well, you just can't literally, get to the answer right away. So you have to do a little bit of trick. In this case, what you can say that adding terms from 0 to 3 would just mean you add the 0th term plus the terms from 1 up to 3. Okay, that's the general approach we're going to take here. Okay, so I'm going to write the 0th term, so I can break this summation up into the 0th term plus the rest of them. Rest of them will start at 1 and we'll still end up at 3 of I cube. Okay, so the 0th term here is when I is 0. So when you plug in I equals to 0 in I cube, you're just going to get 0. Plus, the summation of I cube from 1 to 3 is again the same formula again. So you're going to use n as 3 in this case because tab bound is 3. So it's going to be 3 times 4 over 2 whole squared. So you see the numbers are different. If you were to evaluate this sum, what would this be equals to if you cancel? Oh, my bad, I gotta turn back to green. So you can cancel this, becomes 2. So 2 times 5 is 10, and whole squared is 100. So area according to this is 100 unit, right? But if you were to evaluate the area according to this guy, you cancel this, you're going to get 2 on top. 3 times 2 is 6, and 6 squared is 36. So there's so much difference here, right? From the right-hand point, we get 100, and from the left-hand point, we get 36. So what is our actual area going to be? You can't find that accurately unless you tend to increase the number of n's you're going to choose. But we know it's going to be somewhere between 36 and 100 because 36 is too low because we're doing an under approximation if you draw the figure. Excuse me. And then for 100, we know it's an over approximation. That's why it's too high. Usually for a function that grows up or an increasing function, you just get f of the right-hand point giving you an overestimate and the left-hand point giving you an underestimate. So I have a question. Can't you just plug in the numbers into the equation instead of using the summation formula? Yes, absolutely you can, right? It's so easy to do that because in this case, we're only using 4. How about on the exam if they ask you to solve for this finite Riemann sum using 20 rectangles? You're going to rot your brain trying to figure out how do you find heights of each and every of those 20 rectangles and then eventually put it. In this case, it was easy. We could just literally put up, f of 2, f of 3, f of 4 like we did and solve. But to generalize this idea to like a lot of different kind of numbers that you can add up, you got to use the summation notation. So unfortunately, the answer is yes, you can use the summation notation, but on the exam, they'll make sure you won't be able to. Okay, so the n is going to be large enough for you to like spend all your time for the exam just solving that particular question, and you don't want to do that. Okay, hopefully that answers your question. And that's it. So this is just another Riemann sum problem. So every Riemann sum strategy is very fixed. So when you're doing a finite Riemann sum, the first thing you always got to do, you'll be given this information that's in the white here. Okay, they'll tell you where to begin, they'll tell you where to stop, they'll tell you which function to use, and they'll tell you left or right. And they'll have another question. Did you just plug in 0 into f of xi to get the 0th term? Yes, exactly. The f of xi here is just I cube, and the first term is the 0th term, aka, so you plug in 0 in I cube, you get here. If this term was I squared plus 4, right, and I plug in 0, my 0th term will be 4. Okay? So it all depends on what you have here in this circle. Okay? Hopefully everything makes sense so far. If you have any questions, please ask me right now. Okay, so we're good. This is just taking everything you need to know for a finite Riemann sum and solving it. That's it. Very simple. Okay? I would encourage you to try more problems because what I want to make sure is everybody has enough opportunity to try at least. So I'll be posting solutions to SFU homework, the one that I just talked about, this one, and then the other UBC homework as well, the workbook that's out yet. So I want to make sure that you guys go to the class if that happens in this much snow. Learn this, try to attempt these problems yourself and see if you can solve it or not, okay? Every time the strategy is always going to be fixed. The moment you have all this information that you're given, first thing you got to find is write the things down that you know. Second thing, you got to find delta x. Third thing, you got to find this. Fourth thing, you got to find f of xi. And once you have all this information, you can compose a right sum or a left sum. So this formula is given out to you. These are the condensed notes that you can use to refer to, when you're still learning the concepts. You don't have to know everything from scratch. You can definitely look back and refer to this, okay? Everybody's good? Now we're going to jump to the next part. That is the infinite Riemann sum, okay? So what if somebody, yes, I'll be posting all these notes. Don't worry about it, okay? When you have, the next thing is the infinite Riemann sum. So what Riemann saw is the more rectangles you put, and the better the approximation will get, okay? And then using that fact, he's like, why don't I just take this whole thing and, take its limit, as you did in the previous course, as n going to infinity. So that right there is called the infinite Riemann sum, okay? So how do we modify this whole thing that we already learned? So for us, the Riemann sum was going to start as f of xi times delta x, right? You know what xi is, you know what delta x is, so you're on the same page with me. And here your I starts at either 0 or 1 or goes up to n or n minus 1, right? So depending upon whether you have a left or right. But think about this very closely, okay? Now, I'm not going to draw anything. I want you guys to follow me and focus. If you are trying to fit infinite amount of rectangles, okay, how much do you think the delta x is going to be? If it's going to be any significant or not, that's the only thing I'm trying to answer. Because delta x is b minus a over n. When n goes to infinity, we're going to get a delta x that is really small. Okay? So now, considering the delta x is very small, if you choose to do the right-hand notation, right? You're going to start at f of a plus delta x, right? You're going to start at that point. That's your first starting point. Well, if delta x is so small, then there's no difference between a and a plus delta x, right? So in other way, you can visualize it this way. If you fit in more and more rectangles into this, the width of each rectangle is so tiny that there's virtually no difference between the left or the right point of that tiny rectangle that you're fitting in, right? So it doesn't matter if you choose the right hand notation or the left hand notation for the infinite Riemann sum, because you're going to eventually end up with no difference at all. Okay? So in this case, I'm going to choose the right hand point. Why? Because it's just so much easier to evaluate using formulas, and it's friendly for formulas, right? So I equals to 1 goes up to n, right? And if you take the limit of this expression as n going to infinity, this right here is equivalent of something we know as definite integral. So now the sign will change to an integral sign, and the bound where the integral starts is just going to be a. The bound where the integral ends is going to be the b end. The inside part is f of x, and this delta x becomes dx. So now this is the equivalency relationship. Okay? So now what we have to understand is that if we're given a definite integral at this point in this course, if you're given a definite integral and they ask you to solve it, you have to convert that thing into a Riemann sum. Okay? And then solve the Riemann sum to get to the answer indirectly. Okay? That's the approach we're going to take. In other words, if you're given a Riemann sum and they want you to try to find out what kind of integral does this Riemann sum represent, so you need to know how to jump back and forth here. Okay? And that's what I'm going to focus here for this part. It's going to be a challenging part, so I want to make sure everybody gets it. Where you're given a certain integral and they want you to convert it into Riemann sum, and then they were given a Riemann sum, they want you to convert it into an integral. Like, it's just the representation. You're not solving them yet. You're just trying to represent them in different ways. Okay, so we're gonna first come up with the integral form. Okay, so the first topic is gonna be integral to Riemann. So let's say I have this integral 1 to 3 of x squared plus 2 dx. Okay, and I want you to find me a Riemann sum that represents this integral. Okay, so first of all, is it going to be a Riemann sum that's a finite Riemann sum or an infinite Riemann sum? It's going to be an infinite Riemann sum because it's representing an integral. Okay, so as you can see here in this formula, the infinite Riemann sum, also known as the definite integral, will be when you take the limit of a Riemann sum expression. Okay, so you got to make sure you remember the limit always stays there. Okay, don't forget about that. So in this case, again, we're going to follow the basic strategy that we know, just how to find a Riemann sum for something that you just kind of want to work with. Here, your A could be figured out here. This is your A bound. This is your B bound, right? So A is 1, B is 3. What's N? In this case, because you're taking infinite Riemann sum, you're going to take the limit of n going to infinity anyways. So you don't have to fix a number for it. What you can do is you can keep everything in terms of n, and at the end, just take a limit. Okay? So we're not going to touch n. N is just going to stay n for infinite Riemann sums because it's going to be taking the limit of anyways. So from this, your delta x is going to be what? B minus a over n. So that happens to be 3 minus 1 over n, which is just going to be 2 over n. So now your delta x, instead of being a number, will be in terms of n. Okay? Because it's infinitely long. So we figured out delta x. The next step was to figure out xi. So xi, by definition, is a plus I delta x. So a is 1, and I is just going to be I. Delta x is 2 over n. So we're going to end up with this expression, a plus 2I by n. Okay, this is my xi. So once I have this, I need to figure out what the function is, right? The function is whatever's right here, right? So the function here, f of x, is just x squared plus 2. So what is f of xi going to be? F of xi is literally when you plug this whole thing in place of x here, right? So you're going to get 1 plus 2I over n whole squared plus 2. Okay, this is super important. Please, you got to pay a lot of attention to this thing, okay? Wherever this a plus I delta x is, right? Wherever you see this whole thing, that gets plugged in wherever the x is, okay? So this 2 that's hanging out there does not get any effect, okay? So if you have the delta x term, which is I over n, that thing accompanied by a constant, that goes with it into the x term, okay? It's up to you if you want to simplify this, but for symbolic representations, they don't ask you to do it, okay? So that's f of xi. Now we have everything we need. We need to put this thing in this form, okay? We got to put the limit down. And the summation stays like this. F of xi now, you know, is just this piece here. So 1 plus 2I over n whole square plus 2. This is just the f of xi times the delta x, and delta x we also know is just 2 over n. So this right here represents this definite integral. Okay? Any questions on this? Of how do you convert a definite integral into a Riemann sum? Just representing. Why is there a 2n? Yes, so 2 over n is because you have f of xi times delta x, right? So this portion right here represents f of xi. And this portion right here represents delta x. Delta x is just 2 over n here. Okay? That's why you have a 2 over n there. So every Riemann sum will have this kind of form. And they would ask you to kind of just jump back and forth from what's happening here. Any more questions on this? If not, we'll begin. The tough part is to actually convert the other way, you know, because everybody gets this part, how to convert an integral into a Riemann sum. Some people tend to like flip out when the other way is asked. Okay, so I'm gonna try to walk you through the next one. So now a lot of symbolic comparison. Let's cook up a problem. Let's say we have limit n tends to infinity of a summation where I have 20 over n times sine of 5 plus, you know, this, and I starts at 1, goes to n, and this is the expression. So we're given this Riemann sum, and we're trying to figure out what definite integral does this represent. Okay, that's the idea. So now we have to kind of, first of all, break this up into different pieces. Now, what we tend to identify here, the checklist, what we want our A, we want our B, and we want our f of x, right? We need to figure out what's A, what's B, and what's f of x. Once I have this, I can write this as a to b of f of x dx, right? That's the end target we want to achieve. So we got to figure out a, b, and f of x and dx. Dx is just going to be fixed. So how do you figure that out is by the knowledge of knowing the previous parts that you did, okay? You know everything that's inside a Riemann sum, it's going to be of this form. Delta x times f of xi, right? That's always going to be this form. So now, if you know this, you know there are two things being multiplied here. Here, the first thing multiplied is 20 over n. The other thing being multiplied is sine of this thing, right? So, which one do you think belongs to delta x and which one do you think belongs to f of x is very evident. It's very clear, right? You know that a delta x has a formula of b minus a over n. So you're expecting a denominator to have an n there, you know, and then the only thing that's being multiplied with a denominator of n here is 20 over n. So here, you can directly say that delta x is b minus a over n, and that is equals to 20 divided by n. Any doubts on this? I want to take baby steps so everybody's on the same page with me. Everybody's good? Or does anybody have any questions so far? Okay, everybody's good. So that's this. And from this, you can clearly see the first condition is b minus a needs to be 20. So keep that in mind, okay? That's the first condition. Because b minus a here, it should be the same numerator over there because n's will cancel each other out. So b minus a needs to be 20. So whatever's that bound here at the bottom, whatever's the bound on top, the difference between those two is 20, for sure. That's fixed. Now the next thing we're going to work on is to decipher what actually your a is, okay? And how we can do that is by the second piece. By second piece, you compared it. You said f of xi is sine of 5 plus 20 I over n. Okay? Is this, right? So what's x of I? X of I is just going to be by definition as a plus I times delta x, right? So we don't know what a is, but we definitely know what delta x is, right? So in our case, our xi needs to look like this. So delta x is 20 divided by n, right? So if you put it back here, just to like make it as an eye candy, because that's xi, right? All of this is equivalent of sine 5 plus 20i over n. How many of you guys can clearly see by comparing these things that a is nothing but 5? Or somebody who doesn't see this, please let me know in the chat. If you direct compare them, just eyeballing it, right? You can clearly see that something was plugged inside a function and that something was a plus 20i over n. That whole thing just ended up and became this guy here. So if you compare these two pieces, what you can clearly see is this a and this 5 are going to be equal, right? So it's kind of like a reverse engineering process that you got to think of. So we are assuming that a needs to be 5, okay? If a is 5, then xi is just going to be 5 plus 20i over n. So it's not always this lined up. People asking me questions. So is it always this easy to see? The easy answer is no. It's not that easy to see. But we're trying to walk through the procedure, right? That's why I have this nicely lined up things to kind of embed this in a procedure that you always follow when you're solving for things, right? So this could be messed up. You got to probably factor a couple things to make it look like the one thing that you want. The easy way to kind of like see it, because you have a delta x as 20i over n here, and you have the same thing hanging in there, right? So you know there's nothing messed up here. But if we had a 20i over n here, and then something else inside, we have to probably factor things around to kind of make it look nicer. But we'll leave that for later. For now, we're going to stick to this, okay? So a is 5. Now, because we know what a is, we know the difference between b and a is 20, so we can directly figure out that b needs to be 25, right? Because we know the first condition how it has to be true as well. The difference between them has to be 20. If a starts at 5, then b has to end at 25 in order to match that condition, right? So we've figured out these two. We've figured out a and b. Now the next thing is to figure out f of x, right? So you got to think it in a reverse way. You're given this piece, Okay, you got to think of this in this way, that I had a plus 20i over n that was plugged inside a function, because a plus 20i over n was plugged inside f, right? And you got sine of 5 plus 20i over n. So what would have been that function that got you here? And the answer here, because I was trying to explain, is very easy. The f of x is nothing but sine x. Right? So all you gotta do is try to match up things so they make sense. If you choose your f of x to be sine x, if you choose your a to be this, if you choose your b to be that, and then write a Riemann sum, it will look like this, exactly like this. Okay? So that's the way you can always check back your answer. Okay? If you were given this information to begin with and you were to write a Riemann sum, it should look something like this every time. So now this Riemann sum represents an integral from 5 to 25 of sine x dx. Any questions on this, please? I know this is kind of like a weird way to understand this, but it's most of the time how I do it is eyeballing it, and with practice you get good at this, right? So if it doesn't make sense right now, it will make sense eventually when you see more examples. So I'm going to send you another supplement copy of the notes that I do. It has different examples of everything that we covered right now. So it'll give you more exposure to what kind of problems you're looking at, what's happening, right? And that's the general idea, okay? Now, the last thing I want to mention is how do you solve Riemann sums, like the infinite Riemann sums, or find the area under the curve. So before going there, I want to make sure everybody's on the good pace with me, right? If there are any questions, please ask me right now. Okay, everybody's good, I think so. That's good. Now we're going to cook up like a final problem. The final problem, the way it's going to be appearing on the exam for both of you guys on SFU and UBC, everybody's going to have this one problem based on the Riemann sum. We already did the finite Riemann sum problem. So like this one is the finite Riemann sum problem. But what if you want to find this exact thing but infinitely? Okay, how do you change this thing? Just for the sake of easier algebra, I'm going to make this function into x squared instead of x cubed. Okay, so we're going to do that here. So one example, you'll be given this. So find from, let's say, 0 to 4, x squared dx. Okay, so now this is how they're giving you the problem. Is this an integration problem? For now, no. In future, yes. Okay, in future you'll know how to integrate things, or you probably know how to do this right now using integration. But for the sake of this course, at this point, they want you to figure out this using Riemann sums. Okay, every integral that you get it, you have to make a Riemann sum for this, and then solve the Riemann sum to indirectly answer the integral. Okay, so that's the approach we're going to take. We're going to convert this into a Riemann sum, and then we're going to solve it. Okay, everything is going to stay the same unless we got to be at the point where we have to plug in the limit. Okay, so same stuff, same strategy every time. Pull down the information that you know. Okay, we know that a needs to be 0 because that's this bound, right? We know b needs to be equals to 4 because that's bound on the top. And then we know our f of x is just x squared. Once we have this thing, we can definitely, because this is an infinite Riemann sum, our n is just going to be n for now. Okay, we're going to put the limit at the end, so we don't have to have a value for n so far. Okay, given that fact, you can figure out delta x. That's b minus a over n. So in this case, it'll be 4 over n. Okay, that's fixed. Next thing you can figure out is xi. So xi is just a plus I delta x, again by definition. A is 0, I is just going to be I, delta x is 4 over n, so you're going to get 4i over n. Okay? So this is what it is. Now, what I want to make sure is, okay, let's just, not make it easy any. We're just going to use the x cube so that SFU people can have help from this. So I'm going to convert it back into x cube. So let's pretend we're still solving x cube. Okay, not going to do x squared. So we got this. Now, if your f of x is x cubed, what is going to be your f of xi? Is when you literally plug this thing into the x, right? So you get 4I over n cube. So it's 4I over n cube. Knowing this fact, what you can do is expand it, simplify it a bit, to just kind of like match your needs. I'm gonna try to like minimize the symbols as much as I can. So for me, f of xi is gonna be, if you expand this, you're gonna get 4 cube times I cube divided by n cube, right? If you put the cube on everything that's being multiplied, you can do that. 4 cube is 64 times I cube just stays I cube over n cube. The reason why I'm writing this way, very specifically, watch this. So I'm going to teach you a trick. The trick works all the time. But for that, you have to make sure you put your f of xi every time in this kind of format. Okay, so what I want you to do is, whatever's being multiplied with I cube, you just keep it on the side. 64 over n cube times I cube. Okay, there's nothing fancy. I'm just writing it this way so that you can clearly see what's happening. Okay, so we got to keep it this way. Now that I have my f of xi, I have my delta x, I can definitely make my Riemann sum, and we'll figure out how to solve it, right? So let's write the Riemann sum first. The Riemann sum is going to be limit of n going to infinity, I starting from 1 going up to n, and then your delta x is 4n times your f of xi is 64 over n cube times I cube. Okay, so we got this. If you want to simplify it a bit, I'll show you exactly how to do it. So this is limit this I starting from 1 going up to n, and then you have 4 times 64. You know, that's, we gotta calculate that. 4 times 64 is 256. So 256. And then you have an n out there, you have an n cube here, that becomes n to the 4 times I cube. Okay, so this is what it is. Now, how do you solve this is another challenge. Okay, so I'm going to give you 2 ways, because there are 2 ways to solve this. Eventually, this is a limit problem, right? So I'm going to put this this expression here, because you can get this constant out of the way, because 256 divided by n to the 4 is just a constant. You can get it out of the way, so you can write this as limit n tends to infinity of 256 by n to the 4, and then you're left with the summation of I starting from 1 up to n of I cube, right? And then by summation formula, you know how to break this down, right? So by breaking this down, you can write this as limit n going to infinity of 256 divided by n to the 4 times, so breakdown of I cube summation is going to be n times n plus 1 over 2 whole squared. Okay, at this point, the job of the Riemann sum is done. That's it. This spot is the spot where you're done with Riemann sum. Okay, whatever's left now is to actually evaluate this limit. Okay, and that's where it becomes hard. Okay, so I want to make sure everybody knows how to evaluate these limits. So there are multiple ways. Okay, there's no specific reason why you want to follow my way, or there's a better way that your prof said, or you found something cool in the book. Completely up to you, whatever you do. At this point, you just have to evaluate this limit with all the knowledge that you have. Could be from your high school, could be from the previous course that you took, or something that you learned before. Completely okay. we're done with the problem, okay? All we got to do is solve this limit, and then we have our answer. So I'm going to talk about how I do it, okay? So let's go there. I'm going to try to lasso this, bring it to the next page, and then from there we'll go on. I didn't need that, but I'll just take. Okay, so what I tend to do is break this into a very simple multiplication, okay? You gotta watch this. Everything here is being multiplied, okay, except the n plus 1 inside. But everything else is just nicely factored as being multiplied. So I'm gonna try to expand this, okay? What I'm gonna do here, of course, this might be a little bit longer for somebody. So that's why I wanna keep your patience here, show you this work, and based on this work, I have tricks that you can follow directly to jump up to the answer, okay? So limit n tends to infinity. This 256 divided by n to the 4 stays here. When you expand the square, you will have a 4 at the bottom. So what I can do is I can take this and write it like this. At the same time, there's going to be an n squared, and there's going to be a n plus 1 whole square. How many of you guys are okay with this? Right? Any questions up to this point? All I did is just factored it all, nicely expanded it out so you can see each and individual factor. Everything here makes sense? Okay, we're good. Good. So now what I'm going to do is, what I want to do is just expand this portion right here. Okay, I'm not going to touch this 256 over 4. If you want to simplify this, you can do so. You can get rid of that 256 divided by 4. I think it's 64, right? Yeah, 64. So we're going to get 64 here if you cancel this, so that we have this nicely hanging out on the side. 64 divided by n to the 4. And if you're trying to expand this part in pieces, I'll expand the square first. Okay, I'm going to expand the square first. So we're going to have n squared hanging out. So far, we have n squared plus 1 squared, which is 1, plus 2n. Good. And I'm going to make this n squared go inside and being multiplied with the whole thing, so I can get a better factor. So still we have a limit, n going to infinity, of 64 divided by n to the 4. Now when you multiply this n squared inside with each one of them, okay, what you're going to get is n to the 4 plus n squared plus 2n cubed, right? That's when the n squared goes inside. So everybody's with me so far. Any questions on the algebra? Okay, I'm expecting everybody's good. Good. Now is where it'll be a little bit tricky. So now I'm going to make this n to the 4, and I want to put it inside and multiply, like divide everything by n 4. So we have a limit of n tending to infinity, 64, times, if you divide the whole thing in the bracket with n to the 4, you're going to be left with 1 plus, because n to the 4 divided by n to the 4 will just cancel each other out for the first term. Second time, you're going to have n squared divided by n to the 4, plus you're going to have 2 times n cubed divided by n to the 4, right? That's what we're going to get. So we've got factor that thing inside. Now all we got to do is simplify this expression a bit. And how we can do that, we can cancel this to make a square at the bottom. We can cancel this cube with it to have an n at the bottom. So this looks like limit of n going to infinity of 64 times 1 plus 1 over n squared plus 2 over n, like this. Okay, so we got this right now. At this point, what we have to focus here is that now we can take a limit. Before we couldn't. Now that we have this expression in a very nice form, when you take a limit of the expression, this 64 stays multiplied to the whole thing. This 1 just stays like 1. When n goes to infinity, 1 over n squared will go to 0, right? Because it's a very standard limit. And so is 2 over n. When you take n as going to infinity, 2 over n will also go to 0. So when you plug in the limit, this expression will just become 64 times 1 plus 0 plus 0, which happens to be 64. Now, was everybody able to follow along with me so far? Good? Any questions? Everything's good. Perfect. So now, this is the longest it can ever get. Okay? The hardest and the longest problem you can ever get so far here is right in front of you. This algebra was supposed to be hard. So now, what is the fast way that I was talking about to jump to the answer right away is hidden somewhere back, okay? You can stop doing all this algebra before and you can jump to the answer if you're very vigilant in following the way I told you, okay? So now, coming back here, when we were trying to compose this Riemann sum, this is the spot where you stop. The moment you can write your Riemann sum like this, where you have a constant, I'm going to symbolically represent as some constant k on top, right? Remember, this k is not the summation here. Summation is in terms of I. Okay, don't get confused. Let's say 256 is some constant k right on top, and then you have n to the power of 4 at the bottom, and you have an I cubed there, right? The answer to this thing is literally whatever that k was divided by the power of n. Okay, 4. You don't have to do all this work, okay, if you're not required to. What you can do is you can jump up from this point onwards to the next way you can write this. Okay, I'll show you exactly what I mean. Okay, just give me a second. I'll show you like the basic formulas that you need for this. I just gotta look for the file. If you have any questions, please feel free to ask me right now. I'm trying to figure out where I had those. I wrote it somewhere. We're trying to. Just give me a second. So here I take the picture of this. And then I send it over to me here. You guys should be able to see it right now. So that's the thing. I'm going to put it in the notes so you guys can actually, use it here as well. So this is the thing that we're trying to work on here, okay? The moment you have this Riemann sum set up in a way where you have, like a limit of n going from 1 to n, the same thing that we had here. You have the same description here. Limit n going from infinity 1 to n, and whatever's inside the summation, if you can write it this way, some constant k divided by, so if you have an I here, you got to make sure that you know this, okay? If you have an I there, the power of n will be 1 more than the power of I. So here I is raised to the power 1, your n is going to be raised to the power 2. This is an I squared here, your n is raised to the power of 3. You have an I cube here, your n is going to be raised to the power of 4. In our case, we had I cube right here, and we had our n raised to the power of 4. That's just like a milestone you can hit in the middle to check whether you're doing the work correctly or not, and that's how you check yourself. Okay, if you are able to get to this point, you're good. So now, using the hack, literally the answer to this limit is nothing but whatever the k was divided by the power of n. So if you were to end up with this setup, your answer is going to be k over 2. In our case, we ended up with k over n to the 4. So our answer is k over 4. This is just a hack, okay? It works like a beauty every single time. It's not required from you to actually solve this limit on the exam. If it's not, then you can literally jump up here. But if you have to, you know the work that we just did, okay? That works. So now we're going to follow this to quickly do one last problem and call it a day. Any questions so far? Nope, I think everybody's good. Okay, so one last problem for today. We're going to talk about this integral from, let's say, let's make it simple. 3 to 4 of x squared plus 2. Okay, something like this. We're trying to find this. To do that, we have to convert it into an infinite Riemann sum first. Okay, so we're going to follow the steps. We know a is going to be 3, b is going to be 4. The moment I know this, I can calculate my delta x. Delta x is going to be 4 minus 3 over n, which is 1 over n. And at the same time, I can also calculate my xi. And that's going to be a plus I delta x, which happens to be 3 plus 1 over n times I. So 3 plus I divided by n. Okay, so we get this, right? Now, once I have my delta x, what is my f of x? My f of x is just going to be x squared plus 2. So my f of xi is going to be just plug in this in the place of x. So we're going to get 3 plus I divided by n whole squared plus 2. We got this. Just to like make it easier, we're going to expand it to make it look nicer. So I'm going to expand it. You expand the square, it's going to be 3 squared, so 9, plus I squared by n squared. Okay, plus we have the last one, that's 2 times 3 times I over n, so that's 6i over n. And you have a plus 2 hanging outside. That adds up with 9 to give you the final f of xi to be 11 plus I squared over n squared plus 6i over n. Okay, so now my delta x that I already know is 1 over n. So my f of xi times delta x, that's going to be inside my Riemann sum, right? Which will evaluate to be what? 11. Let me remove that. 11 plus I squared over n squared plus 6i over n. All of this thing multiplied by 1 over n, right? And we're going to take a summation of this, right? That's the inside part of the Riemann sum. So now if you expand it already and then put it inside, I want to simplify it as much as I can beforehand to put it inside a summation because I want to use the shortcut way. Okay, 11 over n. This is going to be, so again, remember, I want to write it in this standard form. I want to write this as 1 over n cubed times I squared. Okay, just because I wanted to make it look like that. Plus 6 over n squared times I. Okay, so now my Riemann sum, limit n tend to infinity, the expression here from I starting from 1 going to n of this whole guy. Okay, so we're going to get 11 over n plus 1 over n cubed times I squared plus 6 over n squared times I. You can expand this into separate pieces and you can then evaluate it. limit of n tending to infinity of 11 divided by n. That's the first piece. Plus limit n tending to infinity of I starting from 1 going up to n of 1 over n cubed times I squared. That's the second piece. Plus the third piece is limit n tending to infinity of summation I starting from 1 up to n of this last piece here, 6 over n squared times I. So now, this is a spot where you can jump up to the answer using the shortcut, okay? In other words, you have to evaluate this thing by using the summation formula and, do all the mumbo jumbo. But for now, we know how to jump from here to the next trick that we want. Okay, so now very important, to check yourself that you are doing it correctly, you have to make sure that you have the same relationship. Here, in this case, I is raised to the power of 2, and n needs to be 1 more than that, so that's n cubed. Here, I is raised to the power of 1, and n is raised to the square. So we're good so far, right? So now how do you jump up from this to the answers right here is by following the shortcut, right? And the shortcut that we talked about here is only for the terms that has an I, right? So you have an I here, you have an I squared, you had I cubed. It doesn't work for this one, but here the answer is very obvious because you can evaluate this to be 11 over n times, the summation formula for a constant is just n. So this cancels out. This is just going to be the 11, okay? So this first portion just going to give you 11. The second portion you're going to get is for the I squared here. So if you look at this shortcut formula that we talked about, for I squared, it's just whatever the k value is divided by the n cubed, right? Or else you can remember it this way. Whatever the k value here is, in this case it's 1, divided by the power of n, that's 3. So that's 11 plus 1 over 3, and the last piece here, the constant here is 6, the power of n is 2, so the answer is 6 over 2. Okay, so now you have to add up all of these. So you have 11 plus 1 over 3 plus 6 over 2 is just 3. So that's going to be 14 plus 1 over 3, and you can kind of like solve this thing. So that's the answer. So this one using the shortcut way. It saves you a lot of like spending time here and there, and it'll take some time to get used to it, okay? Eventually when you write this everything in this form, you can jump up to the answers right away, okay? That's just the approach that I take most of the time to solve these Reimann sum problems. And I hope you can also take that when you're solving your problems. So now, any questions in this work so far? Yeah, it is so much easier. It just helps you, it'll take time for you to get used to it. So once you get used to it, it's so much faster, right? And then especially for UBC students, because MATH103 has exams in the actual, online system. So you don't actually have to show your work anyway, so you can jump up to the answer right away. So Andy's asking a question, wait, how do you do the first part? So which first part are you talking about? This one, the 11 over n? Okay. So if you think about this, 11 over n is a constant, right? I can show you here. So if you were to take the limit of n going to infinity, summation 11 over n, where I starts from 1, goes up to n. You see there's no I in there. So what you have to do is just take away this whole constant out of this page, okay? So we can write this as limit, because 11 over n is not a constant here. So 11 over n comes out of this thing. You're left with 1 inside and goes here, right? This is a standard summation formula. Sum of a constant from 1 to n is just n, right? So your expression is going to look like limit n going to infinity of 11 over n times n. And you see the n's and n's will cancel each other out. So it doesn't matter even if you take a limit, there's no n's. The answer to this thing will just be 11. Okay, so did that answer your first part? Okay, we're going to go to the next one. So the other one is 6i over n as well, right? So we're going to, how do we go from 9 to 11? Oh, this one, right? Okay, so this is 9. And then this 2 just gets added up here, okay, to give you this 9 here. Because that's, when you expand this thing, that's what you're going to get. Okay, that makes sense for the 11 to 9? Good. So now we're going to go to the 6i over n here, right? So if you were to write this in a separate page, I'll show you. So you're taking a limit of n going to infinity, summation from I starting to 1, going up to n, 6 over n, is it n squared? Yeah, n squared, times I, right? This right here is a standard formula. So if you think of this and look at the notes here, you have an I, you have a k, and you have an n squared. This formula right here is what you're looking at, okay? And the answer to this is nothing but whatever that constant is. So the constant here in this case is just 6. So that 6 divided by, what's the power of n? That's 2, 6 over 2. That's how you get that other part. And then how did I actually get 6i over n? Was when you expand this thing, right? So 6i is just, this expression comes in from when you expand this whole square. You get 3 times, so basically 2 times 3 times I over n. Because the formula for a plus b whole squared is a squared plus b squared plus 2ab, right? So that's the formula we got there, and that's what we wrote. So a squared here is 9 because 3 squared. B squared here is I squared over n squared. And 2ab is where you get the 6i over n from. Does that answer the question? Okay, good, perfect. Any more questions here? Everybody's good? Okay, perfect. Everybody's good. So now, my little tips that you guys should be able to follow along for the rest of the part is actually, so the times, you got to do these problems a lot more times, okay? Riemann sum takes time to master. Well, you can do so once you know the technique and you have these like pieces of notes that are here, okay? So you can refer to this every time you're solving a problem. The strategy is always the same. Okay, you have to find a, b, delta x, xi, f of xi, make the Riemann sum, and then use the knowledge that you gained before to solve it. Okay, the fundamental difference between a left and a right hand Riemann sum is already, we talked about it. So it'll take some time. So practice a lot of problems, see how you can actually navigate through like what's happening. At the same time, if you have any questions, please feel free to ask me on Facebook. Just message me, I'll be able to help you. And that's one of those things. The other ones, for the infinite Riemann sum, it'll take you a lot of time, okay? Just try to bear with it, try to go through this process, just let it hurt your brain a bit to learn how to write Riemann sums as definite integrals and vice versa. You got to make sure you're good at this, okay? There's so many problems in UBC's web work that you see, and I think SFU people will also have it coming for them. So be ready for that. You'll see a lot of them. Just try to grind through the brain and always cross-check your answers. So the moment we arrived to like a definition here, just like here in this case what we're talking about. So we had this, we called our function to be f sine x, we called a to be this, called b to be that. So if that is true, can you actually make a Riemann sum that looks like that? So make sure you reverse engineer and see if you can actually make it to clearly understand, okay? There are multiple answers for, Riemann sums and different ways you can express it. So you got to make sure that you guys know the one that you're doing and it's coherent with what you understood. Again, and then we'll have a question. Are we usually given an integral where we can expand and use those standard formulas? The standard formulas from those, are you referring to the hacks that I told you, like these ones? Okay. This is something that I cooked up, okay? This is something that I do. So this is, I don't know probably if there's a documented way of doing it. But no, it just works this way. So if you're given a definite integral, the process would be to write this up to this step, okay, like this here. Once you have it to this step, where you have an I cube and an n to the 4, it's correct. You can straight up jump from this point to the answer, okay? So you can expand and use these standard formulas or hacks that you can think. They're not standardized because I don't see them published anywhere, but yeah, it kind of works very well with this Riemann sum kind of problems, okay? It's just generic algebra that you do, that kind of helps you. Does that answer your question? Good, okay. So yeah, it'll take some time to like go back and forth through all these topics, but at the same time, we still are going to learn this in the class. So you guys are gonna go to the school, if the snow permits. You're gonna go there, and you're gonna learn all of this. So the point of this session was to reinforce the emphasis of topics that you're gonna learn before, and then you're gonna go there in the class, actually learn it from your prof, solve some problems, ask me, and walk through them with me. That's how you fix a topic, right? So there's still a lot of learning to be done, but at this point, if what I talked about makes 80% sense, at least you're not supposed to understand it or learn it all together, but everything that we followed up should make about 80% sense, then we're all good. Okay, so we're done with the session. If there are no questions, feel free to leave, and thank you so much for tuning in. And you guys are welcome.